All right. So this is a simple explanation of a coding project that I've been working on, which uses the graphics module for Python. So what this is it's a simulation. It's a simulation of a special type of engine which uses what I like to call a medium to make it ever so slightly more efficient. It simulates different parts of the engine, such as the high pressure section and the low pressure spool, and it shows or basically is kind of like a visual aid for how they would interact with each other in this type of special engine. So I'm going to get right into the simulation first. I'm going to run it so that you can see what it's like. And I actually have a diagram embedded into it, which I can use to explain exactly what my idea is and what this medium is. So here's the diagram. It's a cross section of a engine which uses a medium. Here in the front in gray is the front fan. It's what you see when you look directly into an engine. And behind it is the low pressure shaft, which is in green, and the high pressure shaft, which is in blue. So when this fan starts spinning, in this case the median is locked. So both the low pressure shaft and the fan would move at the same speed. However, when the medium is activated, voltage is inputted into the medium. In this case, it's electrorheological gel, which reacts to an increase in voltage with an increase in viscosity. So how that works is basically, let's say I put zero point 0.5 kilovolts instead of 0 kilovolts. The viscosity of the ERG inside this area would increase, and that would allow the low pressure shafts to influence the rotational speed of the front fan more than it would in this situation where there's 0 kilovolts. So let me turn on the engine and show you how that would work. So in this case, I'm going to put the throttle at 20%, and we can see that since the medium is locked or not active, both the low pressure shaft and the fan are moving at the same RPM. However, when the medium is activated, and I've actually created a computer program which automates the application of the voltage, we can see that the low pressure spool is able to spin at a higher RPM than the fan. So why does this make an engine more efficient? Well, the front fan, is the part of the engine which has the longest blades. Longest blades. Because of this, it can only spin at a maximum RPM of 4,000 before breaking the speed of sound. Why is this? Well, if something has the longest blades, that means it has the largest radius of any disk within the engine. And that means that it has the largest circumference out of anything else that's spinning at that rotational speed in the engine. So if something that's spinning at 4,000 RPM with this large of a radius compared to something that is spinning at 10,000 RPM with a smaller radius, they would both have the same linear velocity at the tip of the fan blades. Therefore, they would both not break the speed of sound, but would break the speed of sound if they went any faster. Because of this, the fan in the front is only able to spin at a 4,000 RPM value, whereas the low pressure spool and the high pressure shaft are able to spin at a much higher RPM value before breaking the speed of sound. So this is what I'm trying to depict with this diagram and with the simulation as a whole, is how adding a median in between the low pressure shaft and the fan would allow the low pressure spool to spin at its higher potential and basically use the potential of it being at maximum of 10,000 RPM to make the engine a little bit more efficient instead of keeping these two locked together and only allowing it to spin at a maximum of 4,000, where the low pressure shaft could be spinning faster and providing more thrust. So I'm going to play around with the throttle a little bit so that we can see how the engine would react to changes in throttle. At 72%, the target RPM for the low pressure spool is much higher than the target RPM for the fan. And that makes sense because the low pressure spool can spin at a faster RPM and produce more thrust without breaking the speed of sound, whereas the fan can move at this RPM at this throttle without breaking the speed of sound. So that's what I wanted to show. I hope that's clear enough. If you have any questions, please leave them in the comments. I'd be happy to answer. So now I'm going to lower the throttle a little bit and deactivate the median. And you can see how the engine would react to changes in throttle like that. How I've simulated this is basically I've used some simple equations to simulate the gradient of the RPM of each section, moving up to its target RPM and moving down to its target RPM. So now I'm going to turn this off and go in depth into the code, and I'll show you the background image which I use to make all of this occur. So this is the code. These are the imports. These are the packages that I've imported. Some of these are packages that I've made, while others are built-ins for Python. And this is the variable initialization section. So here, the current RPMs, the target RPMs, and the maximum RPMs are initialized, as well as some other miscellaneous variables. And then we get into the main loop where the controls and everything are simulated. So these are just the text boxes, and this is where they're basically updated every loop. So each one of the objects is updated based on this new value and then drawn out to the window. Then we have this system right here, which is basically the control logic system, where all of the inputs that you could put into the computer and what the computer will do in certain situations. That's basically all it does. It basically reacts to key presses. And for that, I've used a function, or sorry, not a function, a package called, not a special package. This is just from the graphics package. All right, and then this is my favorite part, because this is where the RPMs are actually updated based on the target RPM value and the current RPM value. So the way I've done this is basically with this equation right here, which takes the difference in RPM between the target RPM and the current RPM and multiplies that by a scale factor, in this case 10%, plus or minus a specific noise factor to simulate real life twice. So there are two different noise factors. This is applied even in the fan, although the fan is special because the voltage is also considered. So in this case, each one of the voltage values has a slightly different equation and a slightly different multiplication or percentage that can be used on the difference in RPM. So 4%, 7%, 10%, etc. And right here, this is where the computer automates the application of the voltage. So it's very simple. It basically just takes ranges in the difference in RPM, and based on that, it applies a specific voltage value. So if the difference in RPM was between 600 and 180, the voltage would be 0.6, and so on. And this just undraws all the objects that we drew before so that they can be re-updated in the next round. This is what the background image is. This is the image that does not contain any of the changing variables being printed out. And I made this in Google Slides, actually, with all of these different objects to represent the cross section. So I'll go through it one more time. This is a special engine which uses a medium to increase the efficiency. How it does this is by putting an electrorheological gel or electrorheological fluid, which, when a voltage is applied, increases in viscosity, allowing the low pressure shaft to influence the fan, the front fan, more than it would if the voltage was at a lower value and if the viscosity was at a lower value. The reason that adding a medium in between the low pressure shaft and the fan increases the efficiency of the engine is because the fan has the longest blades out of any other part of the engine. So it can only spin at a maximum RPM value of around 4,000 before the tips of the fan blades break the speed of sound, because it has the largest circumference, because it has the largest radius or longest fan blades. Since the low pressure shaft has smaller fan blades, it can spin at a higher RPM value of around 10,000 to 12,000, depending on what engine you research. So, although it is able to spin at this higher RPM value, in most modern engines, the low pressure shaft and the front fan are directly connected with each other. This means that the low pressure shaft can only spin at a maximum RPM of what the front fan's maximum RPM is, which is 4,000. However, when we add a median, This allows the low pressure spool to move at a faster RPM and get closer to its maximum RPM, which increases the thrust efficiency of the special engine that I've created here. If you have any questions or even any suggestions about this, I would love to hear it in the comments. And thank you so much for watching this. I appreciate it.